Jai Hind students. In the last lecture, we discussed about the satellite link equation. This is the satellite link equation. Actually, when we are talking about the satellite link equation, that equation came from the flux density. Actually, to design a satellite link, we have to derive some equation, and that equation is called link equation, which gives the complete information of the received and the transmitted power between the earth station and the satellite. So it is all about that a source is located in the space at the satellite, which is giving us the radiated power in the form of EIRP, which is denoted by PTGT in this equation. At the receiver side, we have GR, that is the receiving gain, gain of the receiving antenna, and 4 pi r upon lambda whole square, that is giving us the path losses. So this satellite link equation actually giving us the complete information between the transmitting antenna, path and the earth station. So when we describe it in a more clear manner, this is the receiving power at the earth station, where EIRP is the PT, GT, GR is equal to the gain of the receiving antenna, then LP is the path losses, LA is the losses due to the atmosphere, LTA is the loss of the transmitting antenna due to, LRA is the losses due to the receiving antenna. So these all are going to combinedly describe the satellite link through this satellite link equation. So now I am going to told you about the noise. Actually, whenever we will discuss about the communication, noise is the supermost part which play a very crucial role in the designing of any system. Such as if you are using a normal system, then there are two conditions or two atmosphere, means this is the system, this is the internal environment of the system and this is the external environment of this system. Now, as you know that this system have various component, various blocks in this inside part. Each blocks, each circuit, each components have various component like transistor, resistance, capacitance, inductance, and due to all that components, that system also have its own noise due to the non-linearity of that components. That all noises are considered as internal noises. Similarly, as discussed here, atmospheric noise, that external part is related to the outer atmosphere of the system and all the other nearby system performances or the atmospheric conditions such as thunderstorm or hailstorm, they are also going to generate various kind of noises, and that all noises such as industrial noise or atmospheric noise all are considered as external noise sources. So that system noise temperature or system noise consideration are very much crucial consideration here in the designing of a system, because due to the introduction of the noise, the system temperature is also increased, because that temperature is generated by the noise, system noise. So the noise temperature is a useful concept in communication receivers, since it provides a way of determining how much thermal noise is generated by active and the passive devices in the receiving system. Now at the microwave frequency, when a black body with a physical temperature Tp degree Kelvin generate electrical noise over a wide bandwidth, then the noise power is Pn is given by small k Tpbn, where Bn is the noise bandwidth in which the noise power is measured, where Tp is the physical temperature of the source in Kelvin degree, and K is the Boltzmann constant, which value is 1.39 into 10 to the power minus 23 joule per Kelvin. If want to talk in dB, then it minus 228.6 dB. So this is about the noise power, basic noise. What is noise and what is noise, how it is coming from noise temperature. Then to determine the performance of a receiving system, we need to be able to find the total thermal noise power against which the signal must be demodulated. So we do this by determining the system noise temperature by Ts. So here you have to understand this thermal noise. As I told you in the previous one, there are various type of noises in external noise such as atmospheric, industrial. Whether in the internal noise, there are flickers and thermal noise. When you are taking a resistor R and if you are applying any power across to it, and due to applied power, that resistance will create some kind of heat due to the resistance of this component. That particular heat up is known as the thermal noise actually. So the noise created due to the resistance of any component is known as thermal noise. So here we are going to consider that part. So thermal noise, we are going to describe the thermal noise temperature of a system for which we are designing this Ts. So if the overall end to end gain of the receiver is GRX, GRX is the ratio, not in decibel. Basically GRX is the ratio. So that is end to end gain of the receiver. And the narrowest bandwidth is Bn Hz, then the noise power at the demodulator input means at the receiver side, Pno is equal to KTS Bn GRX, where GRX is the gain of the receiver from RF input to demodulator input. So similarly, noise power referred is input is Pn, Kn. So sir, now to determine the performance of the receiving system, we need to able to find the total thermal noise power against which the signal must be demodulated. So we have to calculate the Ts. So when we are talking about this Ts, means you have to find out overall end to end gain of the receiver, and that is GRX. So with respect to that, Pno is equal to KTS Bn GRX, where GRX is the gain of the receiver from RF input to demodulator input. Similarly, the noise power referred to the input of the receiver is Pn, where Pn is equal to KTS Bn, where Ts is the system temperature. Matlab means here you can know that you are here talking about a particular system. So let the antenna deliver a signal power of PR watt to the receiver RF input. So when it is delivering the PR watt, means the signal power at the demodulator input is PR GRX, because GRX is the gain at the receiving end to end gain. So representing the power contained in the carrier and sideband after amplification and frequency conversion within the receiver. Hence the complete, because I told you, you are always going to find out the C by N ratio. The carrier to noise ratio at the demodulator is given by C by N is equal to PR GRX upon K TS Bn GRX is equal to PR upon K TS Bn. Means this is the earth station receiver. As per this definition or as per this calculation of system noise temperature from here C by N, you are going to design this receiver station, earth station receiver. Here you can see that this is the earth station satellite, antenna, which is getting the signal from the satellite. After completing the complete link equation part, the PR is the receiving power. When it comes to the low noise amplifier, that low noise amplifier gain is GRF, then a band pass filter, with a mixer of local oscillator and the gain of that mixer is GM. Similarly, a band pass filter and then a intermediate frequency amplifier GIF and intermediate frequency output. So here you can see that in the receiver section part, you have various amplifiers and you have to combine all that amplifiers or the gain in a single equation to calculate. So how it is going to happen? That the front end of the receiver is the mounted behind the antenna feed and convert the incoming RF signal to first intermediate frequency range of 900 to 1400 megahertz. This part. This is the first part of the earth station, just behind the antenna. So this allows the receiver to accept all the signal transmitted from a satellite in a 500 megahertz band at C band or KU band, for example. Then the RF amplifier has a high gain and a mixer is followed by a stage of intermediate amplification, intermediate frequency amplification. So this section of the receiver is called low noise block converter. Means this complete block is known as low noise block converter. Actually, that low noise amplifier is just amplifying whether this part is down converting the frequency in the intermediate. That's why it combinedly it is known as low noise block converter. Now LNB. Now the 900 to 1400 megahertz signal is sent over a coaxial cable to a set-top box receiver that contained another down converter and a tunable local oscillator. Then the local oscillator is tuned to convert the incoming signal from a selected transponder to a second intermediate frequency, which is for the another down converter. Now the second intermediate frequency amplifier has a bandwidth matched to the spectrum of the transponder signal. Direct broadcast satellite TV receiver at KU band use this approach with the second intermediate frequency bandwidth of 20 megahertz. So you can see here the simplified diagram. This is the first part. That one is the down converter, low noise down converter just behind the receiving antenna. After that, from here, the second part started. This is the part of set-top box. Here actually we are using the example of your D2H system, as we are taking an example of your direct to home service, in which you can see that you are placing a antenna on your roof and the another part or box which is known as set-top box is located in your room with the TV. So that is the part where that is on the roof. This part is in the room. So now this is the another second down converter with a tunable channel select filter. Then the second local oscillator tunable, because that are tunable, because otherwise you cannot tune the signal for a fixed frequency or down convert it for the second intermediate frequency amplifier. Then the demodulator and the baseband output. So this is the simplified diagram of a earth station receiver by using this link equation. So as you can see that in this complete diagram, we are having a number of amplifiers such as this LNA, then first IF amplifier, then this mixer, then second IF amplifier. But when you want to calculate this complete system temperature, you have to take the equivalent noise temperature of this complete amplifier system. Means you have to calculate the system noise temperature, as if the Tin is the temperature, TRF is the another one, gain is the first stage, then the noiseless mixer stage, noiseless intermediate frequency amplifier stage. Each stage is adding its equivalent noise source. So all these gain are going to be considered here. Means noise model of the receiver. You are creating the noise model of this receiver, in which you are going to remove all physical parameters. You are only representing the individual blocks which are creating any type of noise, and you are here taking that calculation from this side. In this you can see that these are the different portions. Each portion is giving equivalent noise source, And you can see that the equivalent circuit in figure can be used to represent a receiver for the purpose of noise analysis. The noisy devices in the receiver are replaced by the equivalent noiseless blocks with the same gain and the noise generator at the input to each block, such that the block produce the same noise at its output as the device it replaces. Means you are taking this LNA GRF, you are replacing by this. This is the equivalent noise temperature, this is the gain. Similarly for other steps also. Then the entire receiver is then reduced to a single equivalent noiseless block with the same end-to-end gain as the actual receiver and a single noise source at its input with temperature Tn by this. Means the total noise power at the output of the intermediate frequency receiver figure is given by. This is the total noise power that is calculated with the equations. For the Pn is equal to GIF-K TIF Bn, then GIF Gm K. This is due to this second stage, that IF wala part coming from here and this RF part is coming from here. So we are going to consider all these points where GRF, GM and GIF are representing the respectively the gain of the receiver RF amplifier mixer, intermediate frequency amplifier, tuned radio frequency amplifier, and are the equivalent noise temperatures. So Tn is the noise temperature of the antenna measured at its output port. So this is the output. How it is going to achieve? You can see here, noise model of a receiver with a single noise source Ts, noise temperature at a input to a noise loss power incident gain to the receive. Means that complete block is summarized in this block, where system noise source is Ts, Tn is the antenna noise temperature, gain are multiplied GRF, GM, GIF, and noiseless receiver giving the Pn. That formula is this. Now, if equivalent noise sources in figure have a system noise temperature Ts, where Ts is equal to, now in this part you are talking about the noise power. Here in this equation we are talking about the noise temperature. So by deriving that part, Ts is equal to TRF plus Tn plus Tm upon GRF plus TIF upon GM GRF, but K Kelvin. So this is coming from this equivalent part, in which you can see that this is designed as per the power, this is designed as per the temperature. So this is all giving us the complete information of noise calculation for system, and by this we get this noise model for an equivalent output source shown in figure and produce a noise temperature by this. TNO is equal to TP1 minus G1K, where G1 is the linear gain less than unity, not in decibel, for attenuating devices or medium, and Tp is the physical temperature in degree Kelvin. So for an attenuation of a dB, the value of G1 is given by G1 is equal to 10 to the power minus a by 10. This formula is very important. Many times university ask that if the gain is this, Tp is this, what is the value of noise temperature value of the system? So you have to identify this equation also, this equation, that all equations are going to use in the numericals for the system. So these are the system noise temperature. So if you understand all these things step by step, so the equivalent noise circuit as in the figures can be used to represent a receiver for the purpose of noise analysis. The noisy devices in the receiver are replaced by the equivalent noiseless block with the same gain and the noise generator at the input to each block, such that the block produce the same noise at its output as the device it replaces. Then the entire receiver is then reduced to a single equivalent noiseless block with the same end-to-end gain as the actual power and the single noise source's temperature with Tn. So this is the summary of this complete system noise temperature calculation. In the next part, we are going to calculate the G by T ratio, gain to temperature ratio. Actually, in this complete discussion, we already discussed the link equation. We find out the C by N ratio. Now we calculate the system noise temperature. So in the last one, we are going to calculate the G by T ratio, which is the final parameter related to the satellite link design. Till then, thank you.